only at low microwave frequencies, and these tubes cannot operate at high frequencies due to their limitation at those frequencies. Now, we will discuss what are the various limitations of these conventional tubes when they are operating at a very high frequency. We are saying that the conventional tubes becomes very less effective at microwave frequencies when these are used as an amplifier or an oscillator. The limitations of these conventional tubes at higher frequencies is due to, first limitation is inter-electrode capacitance effect. The second limitation is lead inductance effect, and the third is transit time effect. So, these are the three limitations of the conventional tubes when they are operating on high frequency. First is inter-electrode capacitance effect. The capacitance exists when the two pieces of metal are separated by a dielectric, and vacuum, we consider vacuum as a dielectric having dielectric constant value of 1. The elements of triode are made up of metal and they are separated by dielectric material. So, we can say that there must exist capacitance between between the conducting plates, and the existence of this capacitance is called inter-electrode capacitance. We can see in this diagram, in diode we have one anode and cathode terminal. These are the two electrodes, and in between these two electrodes we have vacuum which is acting as a dielectric. So, if we see CAK, it is an inter-electrode capacitance, and in case of triode where we have 3 electrodes, and in these 3 electrodes we can see where we have 3 capacitance like CGC, CAG, CAC. The CGC is capacitance between grid and cathode, and CAG is capacitance between anode and grid. Then CAC is capacitance between anode and cathode. So, these are the capacitive effect. Then we have lead inductance effect. The common lead inductance is the inductance associated with common connection of vacuum triode. This effect is more when frequency of the signal is very high, means this effect comes into the picture when the device is operating at very high frequency, means as the frequency increases, the inductive reactance in the circuit increases, and due to high inductive reactance there is an input matching problem, means we have matching problem if this inductive reactance comes into the circuit. This is the diagram where with each electrode we have some lead inductance like LA, LC or LK or LG. So, these are the lead inductances in the circuit. The lead inductance affects the performance of vacuum triode with most of the input voltage lost across the inductance, and only small fraction of input reach to the terminal for the amplification. So, it is the kind of disadvantage because our overall gain will reduce. So, these inductances from unwanted tuned circuit with the capacitance and parasitic oscillations are produced, and as the frequency increases, this inductive reactance will increase. The next effect is transit time. The actual definition of transit time is the time taken by an electron to travel from cathode to anode. This time is called transit time. At low frequency, this transit time is very small, means it is nearly negligible, means the time taken by the electrons to reach instantaneously to the anode plate from cathode, the time required is very small. But when we are talking about at higher frequency, the transit time becomes very large because the source driving the grid becomes loaded and the gain of vacuum tube becomes less than the unity. So, we can see the effect of transit time, the time taken by an electron to move from cathode to anode. If we are talking about at lower frequency, this time is very small, but when the same circuit is operated at higher frequency, this transit time is very large, which is again a problem in our circuit. So, this loading is due to the dissipation of the power at the grid. The effect of loading is such that the noise in the circuit increases. To minimize this effect, the distance between the electrode is to be reduced and high voltage must be applied, but this will again increase the inter-electrode capacitance. So, we have to trade off between these limitations, means if on the one side if we want to reduce inter-electrode capacitance, then on the other side this transit time will come into the picture, and when we are trying to minimize the transit time problem, then somewhere this inter-electrode capacitive effect will come into the picture. Now, the microwave tubes, they are work on the principle of velocity modulation of electrons. The efficiency of conventional tube is largely independent of frequency up to certain limit, but when this frequency increases beyond certain limit, the several factors combine and they reduces the efficiency of the tube. As we have discussed these effects, these factors like inter-electrode capacitive effect, then lead inductance effect and transit time effect. The tubes that are efficient in the microwave range usually operate on theory of velocity modulation, a concept that avoids the problem encountered in conventional tube. So, velocity modulation is more easily understood from these factor and limits the frequency range of conventional tube. Velocity modulation, the operation of velocity modulation tube depends on the change in the velocity of electrons passing through its electrostatic field, and change in electron velocity causes the tube to produce bunches of electrons, means we are modulating, we are changing the velocity of electrons, and by changing the velocity of electrons we are forming the bunches of electrons, and these bunches are separated by some space through which these electron bunches are drifting, and by variation in the velocity of beam of electrons caused by alternating speeding up and speeding down of the electrons in the beam. This variation is usually caused by a voltage signal which is applied between the grids. Means that first we are accelerating the electrons in the electrostatic field. After forming the bunch, we will retarding these bunches of electron, and we are gaining the energy. The energy is coming out of when we are retarding, they are giving out the energy when we are retarding these electrons in the drift space. So, the first device is klystron tube. Klystron tube is a vacuum tube that can be operated either as an oscillator or as an amplifier at microwave frequencies. Two basic configuration of klystron tubes are multi-cavity and reflex klystron. In multi-cavity klystron, we have number of cavities, and the use of these cavities is just to increase the gain of amplifier. Then we have reflex klystron, which is used as low power microwave oscillator. This is the diagram of multi-cavity klystron. In this diagram, on the one side we have cathode, we have a heater from which the electrons are which are injecting the electrons, and another side we have anode which is a collector, and between these two anodes we have two cavities. First one is buncher cavity, another one is catcher cavity, and these the electrons which is emitting out from the cathode, they form bunches in the buncher cavity and then they drift towards the catcher cavity. At the catcher cavity they are totally retarded and the energy is liberated out from these bunches, and we are getting the amplified signal at the microwave output. In the microwave input we are just applying the RF voltage signal, and at the microwave output we are getting the amplified RF signal. The application of these tubes, they are used as a UHF TV transmitters in troposphere scatter transmitter, satellite communication, radar transmitters, and as a power oscillator they are ranging from 5 to 50 gigahertz. This is the reflex klystron, just a modification of a klystron in which we have just we have one single cavity. From cathode the electrons are emitting and there is a repeller voltage. This voltage is just used to retard the bunches of electron, and first accelerating grid is used to accelerate the bunches of electron, and the repeller voltage is used to retard the bunches, and by retarding these bunches we are getting an amplified signal. So, this is the diagram of reflex klystron. The construction point of view, reflex klystron consists of an electron gun, a cavity with a pair of grids and a repeller plate, and in this klystron a single pair of grid does the function of both buncher and catcher. Earlier in simple klystron or multi cavity klystron we are seeing that we are using two cavities, but over here we are using only one cavity. And the main difference between two cavity reflex klystron amplifier and the reflex klystron is that the output cavity is omitted in the reflex klystron, and plus with that we are using repeller or reflector electrode which is placed at a very short distance from the single cavity and which replaces the collector electrode. The working of reflex klystron, we have discussed that cathode is emitting the electrons and it is accelerated by the accelerating grid with positive voltage, and we are forming a narrow beam. Then these electrons are passing through the cavity, they undergo the velocity modulation which forms the electron bunches. Then these beam is repelled by the repeller voltage, and on the return these electron once again enters into the same grid which act as a buncher, and from that we are getting an amplified signal. So, this is all about the working of reflex klystron. The application areas. The application areas are radar receivers, local oscillators in microwave, then signal source as a microwave generator, portable microwave links, pump oscillator in parametric amplifiers. So, in this discussion what we have seen that the various microwave sources, the reflex klystron, and we have multi cavity klystron and klystron tubes. So, these are the two devices which are acting as a source and they are different in terms of the construction point of view. As we have seen that in klystron, in the multi cavity klystron we have multiple cavities, buncher and catcher cavities, but in reflex klystron we are just only having single cavity which is doing this two function as a buncher or as a catcher. So, these are the various sources.